Here's an interesting problem with an interesting illustration. I'm going to go ahead and highlight some of the important details here and read through the problem. Suppose a square sheet of aluminum, so this is a square with the same length on all four sides. A square sheet of aluminum has dimensions as given by the illustration, and a welder decides to cut out of each corner a square with side length C equals 5 inches. That's this little cutout right here. Then fold up the sides to form a rectangular container with no top and a volume of 80 cubic inches. Question 1, what is the side length x of the new rectangle? And question 2, what was the area of the original sheet of aluminum? So let's go ahead and label C as 5 inches, and that's going to be our little cutouts. And when we fold this box up after those corners are cut out, C is actually going to be what the height of our box, isn't it? The height of our tray. Sometimes when I do a problem like this, I like to just give myself a little sketch to visualize, help me visualize what's going on. So we've got our side lengths x here, x, and we've got our height of 5 inches. And if you can visualize that, that's helpful. We've got a known volume here of 80 cubic inches, don't we? And let's recall how we calculate volume. The volume of a rectangular solid or a rectangular tray like this is going to be the length times the width times the height. And we know in this case that volume is going to be 80 cubic inches. And we'll save our units to the end here. Length on this diagram might be this one right here. Length is that dimension from there to there. Width might be this dimension right here from this side, this end to that end. And height is up here. Our height is known as 5 inches. So let's plug those values into our formula here. So the volume is equal to length is x times width, which is also x, times height, which is 5, and that's all going to equal 80 as our volume. We can write x times x as x squared, so x squared times 5 equals 80. And then usually in an expression like this, we'll put the number before the variable, and so let's rewrite this as 5x squared equals 80. And we're starting to have something that looks like we might be able to solve it. And we're going to use a quadratic equation to solve this problem. Quadratic meaning simply that we've got a square term. Our x squared is part of the equation, and that will make this a quadratic equation. So I'm going to bring that up to the top here. We have 5x squared equals 80. Now when we solve quadratics, we like to get everything on one side of the equal sign and 0 on the other side. So we're solving for a situation where the equation is equal to 0. So how are we going to do that in this case? We've got 80 on the right side of the equal sign, so let's move it to the left by subtracting 80 from both sides. And that gives us 0 over here and 5x squared minus 80 over here. So 5x squared minus 80 equals 0 is our new equation. Another important step in solving equations like these is to see if there's anything that we can factor out, anything that we can divide out of each of the terms in this expression. We have 5x squared and 80, or negative 80. Is there something that goes into both of those terms evenly? And there is, isn't there? We can divide out a 5. And so we can rewrite this expression as 5 times x squared, because 5x squared divided by 5 is equal to x squared, minus, and then 80 divided by 5 is equal to, guess what it is? It's 16. And so now our new equation is 5 times the quantity x squared minus 16 is equal to 0. We want to continue to factor here, and you may recognize this x squared minus 16 as a difference of squares. That's one of the sort of special cases in factoring quadratics, we have a square term minus another square term. And we can factor that as the square root of the first term, so the square root of x squared is just x, and then plus the square root of the second term, the square root of 16 is 4, and then x minus 4. So let's bring our 5 back in, and we'll set all of this equal to 0, and we're continuing down our solution. Now, another cool thing to remember is that when we multiply by 0, the answer or result is 0. There are 3 elements on the left of this equation. If any one of which equals 0, the whole equation equals 0 and we would have a solution. Well, we know that 5 isn't 0, so we're going to just kind of forget about that for a moment. But x plus 4, if x plus 4 equals 0, then the whole equation equals 0 and we have a solution. And if x minus 4 is equal to 0, 0 times the other parts of this side of the equation will give us 0 and we have another solution. So we can solve for the two cases here where x plus 4 is equal to 0 or x minus 4 is equal to 0. And in either case we have a correct solution for x. So solving the first one, we can subtract 4 from both sides, and that's going to give us x is equal to negative 4. And solving the second one, we can add 4 to both sides, and that's going to give us x is equal to positive 4, or just 4. Now, let's remember what we're solving for here. We're solving for the lengths of a rectangular shape here. And is it possible to have a length that is a negative value, negative 4? It is not. In the world that we live in and the way that we've described it, a negative value cannot be the length of a solid shape like this. And so we can rule out this first answer as it's a valid solution for x, but it's not a valid solution for this problem. We have to have a positive answer. And so our second solution for x gives us that. And so we have solved this first part of the problem. The side length, x, of the rectangle, of the new rectangle, is equal to 4. X is equal to 4. And let's add our units here. We're in inches throughout, and so x is equal to 4 inches. These are linear. This is a linear dimension, so it's not square inches or cubic inches. X is equal to 4 inches. Now, let's go back to the second question. What was the area of the original sheet of aluminum? So we can plug our newly found x value in over on our diagram here to the left. And we can say that x, we know that it's equal to 4 inches, and down here it's also equal to 4 inches. We know that c is equal to 5 inches, and c over here is 5 inches, and c down here is 5 inches. And so our side lengths of this square, we add up the 5 plus 4 plus the 5, that's going to give us 14 inches in this dimension or direction, and 14 total inches in this direction. So if we draw ourselves a new little sketch down here, our original sheet with the corners all cut out, but our original sheet was 14 by 14 inches. And to find the total area of that shape, we multiply 14 by 14, 14 times 14, and that's going to give us a total of 196. We have inches times inches, and that's going to give us square inches. We could also write that as inches squared. And that is the second solution. The area of the original sheet of aluminum, the area is equal to 196 square inches, and that is the solution to this problem.